Welcome to the Explainer. Today we're taking a pretty wild ride. We are going from the mind-bending, honestly almost unbelievable laws of theoretical physics straight into the grounded and often very harsh reality of modern engineering. We're looking at a technology that governments and massive tech giants are just pouring billions of dollars into right now. It's a technology that literally promises to reshape our world: quantum computing. But with all the buzz going around, we have to ask, where exactly does the science fiction end and the actual science begin?
I want you to start by just imagining this for a second. What if a computer could exist in two different states at the exact same time? It sounds like a total paradox, right? But this one provocative question is the absolute beating heart of quantum technology. It is the ultimate promise that has sparked this massive global race and, honestly, unprecedented economic hype. We're talking about a paradigm shift so profound that it kind of makes the leap from the abacus to the modern microchip look like just a tiny little baby step.
Section 1. The limits of classical computers.
So why do we even need to look beyond the massive supercomputers we already have? Well, it's because we're hitting a physical wall, literally. Down at the atomic scale, classical physics just breaks down. Our current computers process information using macroscopic circuits, and as we shrink those down to boost computing power, we are getting uncomfortably close to the size of individual atoms. So, instead of fighting those weird microscopic rules, quantum computing actually uses them. Think about it like this. Classical computers use bits, which are strictly binary. It's like a coin sitting on a table. It's either heads, a 1, or tails, a 0. But a quantum computer uses qubits. Imagine taking that same coin and spinning it on the table. While it's spinning, it's a blur, right? It's a probability of being both at the same time. This allows qubits to perform immense parallel calculations through a process called interference, completely leaving classical bits in the dust.
Section 2. Qubits and quantum magic.
It's honestly awe-inspiring when you realize we are harnessing the fundamental behaviors of the universe just to do math. The first trick up our sleeve is superposition. Instead of just being a rigid, boring 0 or a 1, a qubit exists as this complex, overlapping combination of both. Think of a classical computer trying to navigate a maze. It tries one path, hits a dead end, goes all the way back, and tries the next. It explores sequentially. A quantum computer, in superposition, it's like a wave of water just flooding the entire maze all at once. It explores vast computational spaces simultaneously. It's not just a random 0 or 1, it is a highly coherent overlap of possibilities. Now, the second piece of magic is entanglement, and this perfectly illustrates why quantum computers scale so aggressively. Entanglement is this bizarre phenomenon where the state of one qubit becomes fundamentally linked to another, no matter how far apart they are. If you measure one, boom, you instantly know the state of the other. Because of this, adding just one more qubit actually doubles your processing power. It builds a massive, multi-dimensional workspace. To put that into perspective, a system of just a few hundred entangled qubits can represent more simultaneous states than there are atoms in the entire observable universe. That is just wild.
Section 3. Potential applications.
Okay, so what do we actually do with all this multi-dimensional calculating power? We target the big stuff. Problems that classical computers could never solve, even if you let them run for a billion years. First up, complex optimization. We're talking about perfectly balancing global financial portfolios or routing worldwide shipping traffic in real time. Second, simulating nature at the molecular level. Classical computers really struggle to simulate even simple molecules accurately, but quantum computers natively speak the language of molecules. This opens the door to discovering new battery materials or even life-saving drugs without running endless physical lab trials. And third, the elephant in the room, cryptography. Specific quantum equations, like the famous Shor's algorithm, have the theoretical ability to just shatter the math that currently secures our entire global internet.
Because of these profound, world-changing applications, the economic stakes are absolutely astronomical. A recent report from the World Economic Forum projects that quantum computing could generate a potential value of 450 to 850 billion US dollars by 2035. That staggering number really underscores why there is this fierce, massive global race among nations and tech corporations to be the first to achieve a functional, scalable quantum computer.
Section 4. The technological hurdles.
So, if the potential is that massive, why don't we have these things sitting on our desks right now? Well, it's time for a reality check. Building a quantum computer is arguably one of the most difficult engineering challenges in human history. Just look at this number, 15 millikelvin. For many common quantum architectures, specifically the superconducting qubits used by companies like IBM and Google, the processor has to be cooled to 15 millikelvin. That is literally a fraction of a degree above absolute zero. It is significantly colder than the vacuum of deep space. They have to use these massive, incredibly complex cryogenic systems just to keep the chip functioning. But why go through all that trouble? Why does it need to be so cold?
It all comes down to one word: decoherence. This is the fatal flaw of current quantum systems. You see, qubits are incredibly frustratingly fragile. Any interaction with the outside world, a stray photon, a tiny microscopic fluctuation in temperature, even a weak magnetic field, causes the qubit to lose its quantum state. It basically collapses back into a basic, boring classical bit. That extreme deep space cooling, that's our way of shielding these qubits from the environment, trying to prevent decoherence just long enough to actually run a calculation.
Section 5. Milestones in research. But hey, despite these monumental, almost impossible hurdles, this mind-bending theory has slowly morphed into laboratory reality over the last few decades. It really started taking shape back in 1981 when physicist Richard Feynman famously proposed the basic model. He essentially argued that to simulate nature, you need a quantum mechanical computer. Fast forward to 2001, and researchers successfully ran Shor's algorithm on a tiny little 7-qubit system to factor the number 15. It was a small proof of concept, sure, but a massive deal. Then, a huge leap in 2019. Google actually announced quantum supremacy with its 53-qubit Sycamore processor. They demonstrated this highly complex calculation in just 200 seconds, a task they claimed would take the world's fastest classical supercomputer something like 10,000 years to complete.
Section 6. Hype versus reality.
Now, when you hear something like 10,000 years reduced to 200 seconds, it's super easy to jump up and say the revolution is already here, but we really need to take an objective look at the hardware. Winfried K. Hansinger, a physicist who actually operates quantum computers, recently summed up the current state of the industry pretty bluntly. He said, "They are all terrible. They can't do anything useful." And honestly, that brilliantly tempers the hype. Why are they terrible? Error rates. Current systems are incredibly noisy. To do truly useful commercial work, like breaking cryptography, we don't just need 50 or 400 qubits. Researchers estimate we might need millions of physical qubits just to error correct enough to create a single stable logical qubit. So yeah, we are definitely still deep in the prototype phase.
There's also this really fascinating paradox when we look at the environmental and economic side of things. Right now, there are massive, high operating costs and insane energy consumption required just to power those deep space cryogenic coolers. But this is completely contrasted with the long-term dream of green IT. If we can actually achieve true algorithmic efficiency, a quantum computer could theoretically solve complex problems in seconds, problems that would otherwise force classical supercomputers to burn through massive amounts of electricity for months on end.
So, what is the big takeaway from all this? Quantum computing is for sure no longer just a thought experiment in theoretical physics. It's a tangible, albeit infant, technology. The leaps we are making are historic, but the engineering mountains we still have to climb are equally massive. And as we edge closer and closer to this reality, I want to leave you with one final, kind of provocative thought. Because of the staggering cost and the massive infrastructure required to build these machines, we are facing a potential quantum divide. When the age of quantum computers finally does arrive, when the power to simulate new medicines, perfectly optimize global finance, and break encryptions is actually realized, who's going to control that technology? And how exactly is that going to shape the socioeconomic future of everyone else?